Hey friends, I want to introduce a new sponsor to you, HMA VPN. It's a VPN you can count on. As you know, I do a lot of travel and I tend to connect to a lot of untrusted wireless networks, and I probably shouldn't, but I can use HMA as the world's largest VPN service. It offers the most server locations worldwide, covers 190 countries. There's always a server nearby. Doesn't log your IP address, and it allows me to connect 5 devices simultaneously. It works on basically all platforms: Android, iOS, Mac, Linux, Windows, routers, wherever. It's actually been completely redesigned recently to make it even simpler and more fun to use. And there's even a smart kill switch that'll turn the VPN automatically on when you launch sensitive apps. Here's your call to action, my friends. Try HMA VPN risk-free with a 30-day money-back guarantee. This deal is for Hansel Minutes listeners. That's hmavpn.com/offer-Hansel Minutes. That's hmavpn.com/offer-Hansel Minutes. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Freya Holmér. She makes amazing math visualizations that are all over Twitter, and you do Twitch streaming. I've seen also math for game dev. You have like a 4-hour improvised live course. You just live and eat and sleep math and game dev. It's so amazing. Thank you for coming on the show.
Oh, thank you so much for having me.
You know how you bump into somebody on Twitter and you're like, oh, this seems like a nice thing. And then you start scrolling and and it's like, oh my goodness. And then you just infinitely scroll through the media part of their Twitter and you're like, what is going on? How did I not know this person existed? That's how I felt when I started scrolling through your Twitter, because you have all of these really cool visualizations that explain really complicated math problems in a way that I had never seen before. Are you the only person that does this, or is there math visualization Twitter?
I don't know if there's a community for it on Twitter, but I mean, there are some things that I've seen. There's a YouTuber called 3Blue1Brown who does like really cool math visualizations. He goes very in depth on stuff, but he visualizes it in a very intuitive and nice way. So I think that was probably one of my inspirations for doing like math visualizations. But I think the primary motivator for me was just that when making games, there are so many complex systems that interact, and a lot of them are like mathematical or geometrical. One of the ways to debug that, to find out whether something is wrong or not, is to visualize it. And I found that sharing those visualizations with people, or just showing that, it resonates with people somehow. Just seeing the underlying data, seeing the underlying patterns that emerge, sort of. And I think there's a strong appreciation for that.
What do people use to make these animations? And do you know it off the top of your head when that started? Because the first visualizations I ever made would be 20 or 30 years ago. And visualization, when I say visualization, I don't just mean a graph. I mean over time. The first ones I ever made would be like on a TI 83 or a TI 89 calculator. Very one frame every 5 seconds type visualizations. But, when did math animation really start blowing up?
I don't know, really. I remember that there was one math animation that was making its rounds around Twitter that looked really old. It looked like it was made like through some oscilloscope or something. So I guess it's been around for a long time, but it doesn't seem to have been like very well established. Like, you're not going to open a math textbook and see animations, right?
Sure.
But it seems to be pretty obscure at this point, which is kind of why I wanted to make more of it. Because it seems to resonate with people. Like, I just made this very simple animation showing the sine and cosine relationship with the unit circle. Very simple animation of, a vector spinning in a circle, and then showing how sine and cosine, how those functions relate to that vector. And that tweet just like blew up, and everybody was like, oh, why were you not my teacher in high school or whatever? And that seemed to be like, it was not just one person, that seemed to be like ubiquitous in all of the replies. And so I thought that, okay, so given how how much traction this got, given how much people seem to learn just by me playing around with like vectors. Uh, like it seems like there's a space where I could make educational content that looks pretty. And I think that really resonates with people because to many, I think math is just very boring and daunting. And I think that's partially because it's presented in a very boring way.
I feel also as I have a 12-year-old and a 14-year-old, and as I try to get them ideally, of course, excited by math, but worst case scenario, not deeply offended by math, right? Like there's a low bar when you're trying to teach children math here. Like not hating it would be success. The biggest thing that they're having trouble with is visualizing things over time because math is such a dynamic thing. It's the continuum that they can't see. So why are we giving them black and white textbooks and saying, here's, graph X, graph Y, do that, and now visualize it over time? That's a big jump to ask someone to do.
It really is. And I think there's something like that jump, I think is very not underappreciated. I don't know the word for it, but like showing a graph of something, like a trajectory, and you have time on some axis, like that, like conceptualizing that is pretty difficult because you have this layer of abstraction where you've like mapped out time over an axis, which is kind of weird. Like it's probably difficult to get a grasp of that unless you intuitively know these things very well. So I think making that connection takes time. But being able to show an animation next to that and then showing a line that moves with time, then immediately you can see that, oh, this is connected to time. This is not a spatial dimension or whatever.
That's a really interesting point, right? Like we have all this three-dimensional stuff that we try to present to people on two-dimensional medium, and time is a fourth dimension, and we still try to show that to people in 2 dimensions. And it's like, oh, well, we can't make it move, so let's put it on an axis and let them, animate it in their heads?
Yeah, exactly. And I mean, there's still use of having it on an axis. It's just that it's not the best way to introduce something to people.
Mm-hmm. So these are gorgeous, and they feel very... They are reliably the same kind of style and font, almost as if there's like a Microsoft Word or a Microsoft Excel of math animations. Are you using Mathematica, or is this a thing of your own creation?
It's kind of my own thing. It's a long story. So
if
I have
only
a
we had a
background in game
podcast,
development.
that would be amazing. You could tell that long story.
Yeah. So my background has been very strongly in like knee deep in game development for a very, very long time. So that's sort of been my approach to everything I make. And, I would always say that, or I've always considered games to sort of be probably one of the most, or if not the most advanced, media form we have today. It incorporates so much from from radio, from movies, from theater, from even arcade games or playing physically with people or whatever. Like it incorporates all of these things in one place. So the amount of things you need to know in order to make a game or a complete experience, it's massive. There are so many things you need to learn when it comes to, visuals, when it comes to audio, when it comes to design, when it comes to even, all the business stuff with marketing and all of that. And the way I've navigated games is usually through the lens of an indie developer. So that means making an entire game on your own. So that means I have to learn all of these separate things. And I think many people sort of narrow down their scope to, either I do programming or tech, and then they just do that. Or I do art, and then I just do that. And then there aren't a whole lot of people, I think, who spread themselves wider across the whole spectrum of things you can learn. So I think one thing that's happened is that given that I've sort of spread myself across all of these different, aspects of making games, I sort of have a view of what would a game version of a math animation be? So then it's not just about showing what sine and cosine is. That's what textbooks do, right? They have this, they show the curves and then they kind of leave it at that. But, what happened to art direction? Where did that department go? What happened to marketing? How do we present this in an interesting way? How do we make sure that, this is engaging? And I think that's something that's strongly lacking in, textbook math. So I feel like I approach these things as if they were like an interactive video game experience.
So right now you're using primarily Twitter for your kind of like letting us know it's the fire hose of all the things that Freya is working on. But I want to like stop the GIFs and I want to seek forward and I want to go forward and backwards. I want to interact with these. I want them to be a video game. But then when I see what my kids are learning, it's just like they'll have an iPad and I'm like, oh, we're learning math on an iPad. And the teacher gave them a PDF. So there's this gap, either like your GIFs are read only and I can't interact with them or play with them. And then my children are on an iPad or a tablet and it's just a PDF, which serves no purpose at all. We're definitely not playing math games right now and really playing with this information.
Yeah. I think there are a lot of like interactive math things out there as well. So usually they're web-based. Mine are not, which is why I haven't really done interactive stuff. But I think in my case, I think I stuck to Twitter because that was probably my biggest platform. And I got most traction there and I have the biggest reach. And there's no interaction on Twitter in terms of like interacting with, graphics. So, so I kind of just like stuck to making animations, but I've also found that I feel like interaction is a tool like any other, right? And you don't have to use interaction. And if I can get a concept across without interaction, that's better than having people have to interact with that thing. So I feel like just being able to scroll through Twitter and lazily look at something and learn something that's a good thing, I think. But if they would have to pull some handle, then that requires more time and attention from them. But yeah.
No, that's a very good point. So how are you making these? Are these little Unity projects? You just like, oh, I just had an idea for an animation, file new project Unity. Or is this in your engine?
So this is in Unity. I do a scary amount of things in Unity that I shouldn't do in Unity, but here we are. So I kind of started out, let's see, where did I start out? I think I started out making a recorder, basically a way to capture footage inside of Unity and then export that as some sort of animation or an animated GIF or a video. So that's where I started. And then as that one became more and more sophisticated, I noticed that I added a feature that's sometimes called motion blur or like temporal super sampling, where I capture frames between frames so that I get proper interpolation between frames, making it look way more smoother than you would be just capturing single frames. And then I also made it what's called rendered offline, which means that you let your computer take all the time it needs to render a single frame of animation. And then you move on to the next frame instead of live recording, which means that your computer is going to run the game and then try to keep up with the recording, which generally never works consistently. So what happened was that the animations turned out really smooth and they look kind of pretty, just for being like a simple, camera animation or whatever. From there, I started to get interested in making some sort of like math animation. I don't remember which one was the first one. Could have been a sine cosine thing. So I started out thinking, okay, how do you make shapes? Like, how do I make a line in Unity? How do I make a circle? And I didn't really have a good way to do that using the built-in tool. So I started writing my own. And I was also like, at the same time, I was getting really interested in something called signed distance fields. Which I don't know if I should go into details about what that is.
Couldn't hurt, but a little bit.
Well, I started learning how signed distance fields work and how you can use those to make two-dimensional shapes in a very nice way. And from that, it kind of grew, especially as that tweet exploded. I kept working on my vector rendering library, and it grew into something that is pretty sophisticated at this point. So that's kind of the route that I took, and combining the recorder tool that I made and the vector animations, making these animations make them look like they have twice the frame rate, even though they're all 50 FPS. But given that they have this motion blur or interpolation between frames, it looks super smooth, which is kind of a trick to make it look better than it quote unquote actually is. But yeah,
that is really interesting because I'm like, for example, I'm looking at your animation, and I'll put all of this in the show notes, which is the area of a circle one, where you have a circle and it unfolds kind of. I keep staring at it because a circle turns into a triangle, and you keep watching it, and you go, Oh, is that how it works? Like I kind of see what's going on here, but it is preternaturally smooth. And I just assumed you were using Camtasia, but you're right. Like forcing the computer to put all these frames on the screen in a frame buffer and then capture that, it just seems silly. You should just generate them directly, which would explain why they are so smooth. You don't drop a frame.
Yeah. I mean, I do, when I make them, I usually have a slider that I can pull.
Mm-hmm.
So while I'm making them, I can interactively, scrub the time of that one to, figure out how it looks at a given point in time.
Mm-hmm.
So it does render in real time without the motion blur. But as soon as I want to have that motion blur, it takes like, depending on how good of a quality I want, it can take like a minute or two to render a single one.
And is that motion blur something that just humans want to see? Like it looks weird without it, or does it add information?
It adds a lot. So generally if you look at like a 60 frames per second animation, the problem is that you get incorrect information between the frames, right? So you have a dot. Say you have a dot that is moving left and right, and you're looking at this animation at 60 frames per second. When it goes from one frame to another, it renders that dot for 1 divided by 60 seconds,
Mm-hmm.
and then it skips to the next frame where the dot is in a different place, right? Mm-hmm. But what we're trying to emulate is that dot moved from one position to another, but frame by frame, it's actually teleporting, right?
Oh, yeah, it is. I guess it would, depending on all kinds of things as far as DPI and PPI of the screen, et cetera, et cetera.
Oh yeah. But presuming it's moving quickly, then
Right.
you will likely have a large gap between those.
Oh.
So what happens is that for 1 divided by 60 seconds, you will look at incorrect data most of the time because it will be stuck for that amount of time until you hit the next frame, right? So if you compare an animation that has motion blur and one that doesn't, the one with motion blur obviously looks much, much, much better. And it looks so much smoother because then you don't have that incorrect data anymore. I don't know if you worked a lot with VR and some of the techniques they've used there to help prevent this.
I haven't done it, but I do have 3 different VR headsets here in the house, and I'm looking at an HTC Vive Pro right near on my desk here. So I have familiarity as a user.
Oh, gotcha. Okay. So there's a similar technique you can do to, so in my case, like blending between frames using motion blur, that is kind of like I'm interpolating between those frames and I'm averaging, all the data between those two states. Mm-hmm. And that gives you a much more smoother and much more realistic view of what it would look like if you saw it in reality, right? Mm-hmm. There's a neat little trick you can do VR actually, or actually outside of VR too. So the problem is, again, that you're showing incorrect data. But instead of interpolating it, you could just not show data. And that's something you can do in VR, for instance, to make it look smoother than it actually renders. Because in VR, your head movements and everything is really important to have tight, because otherwise you're going to get nauseous. Mm-hmm. So what they do is that they show the frame, and then they turn it off before showing the next frame. So they just turn off the display. It's completely black. And then they show the next frame for a very, very short amount of time, and then they turn it off again. And just by doing that, it looks much smoother. But it's kind of an interesting, it's a super interesting way that your brain sort of fills in the gaps there.
So you're saying that they would rather show you nothing, and your brain would rather see nothing than see wrong information?
Yes, it looks much better. You can actually do this without VR too. I do have an animation on that. Heck, I forgot where I put it, but I can probably dig it up at some point. Okay. I could dig it up now if you want to.
No, dig it up later and put it on Twitter, and people who are listening to the show will have a reason to go and follow you on Twitter.
Yeah, all right. It is on Twitter somewhere, very deep.
Well, we'll go looking for it.
Oh, wait, I found it. There we go.
Impressive. You can put it in the chat right now.
That's the motion blur versus not. So the left one does not have motion blur, the right one does.
Wow. Okay. So what's interesting, I'm looking at this, and I'm going to put this in the show notes so you as well who are listening on the show will be able to see this as well. The one on the right feels very consistently blurry and natural. One on the left feels very, I don't know if the word is jitter, but my brain is seeing almost like there's another white dot. It's like there's more dots. As this dot moves through the sine waves, it's different each time because I feel like I'm running at one sync and it's running at another sync, and my brain is trying to figure out, like, are we at what frame rate are we at? And we're fighting. My brain's fighting with itself to try to see that.
Yeah, it's very effective.
Hey, folks, I'm taking this episode to advertise for other podcasts. If you enjoy stories about the people behind the technology that we use, you should check out the Greater Than Code podcast. They focus on the human side of software development with stories of diversity and inclusion, accessibility from people that you don't normally hear from. Search for Greater Than Code in your favorite podcast app or check out greaterthancode.com.
I also found the other one. So that one is not the one that turns off the pixels between. That one is just the motion blur and the interpolation.
Okay.
And that's the one that I use in my renderer. Anyway, this is the technique they use in VR, but in this case, it's outside of VR. So this is an example of using a very low frame rate. I think this is like 12 FPS.
Right.
And the lower one is also 12 FPS, but the motions, like the lower one looks so much smoother, right?
Yeah, so it is blinking because you're doing it on purpose. It's strobing effectively because you're trying to make the point. But if you ignore the strobing, it doesn't. It feels very consistent. It has a heartbeat to it, while the standard one is just teleporting, as you said before.
Exactly. So what happens is that the trade-off is that your display, the net effect is that it's going to look darker when you have this low persistence.
Interesting. I know that when you watch 3D shows, they're flipping the things back and forth. 3D movies, it has less luminance because they only have half as much brightness going into one eye as they flip 3D back and forth.
Oh yeah, exactly. Yeah.
Interesting. Okay. So this is interesting because now you're kind of combining neuroscience and how the brain works with how the computer is limited in displaying pixels, and you're combining all of that with math. That's a lot of stuff that one needs to understand in order to be effective in this world. We're asking a lot of young people to start out.
Yeah, you certainly don't need to explore all the stuff that I've done. It's mostly because I've been very curious to do that in game development, and because I like being able to do all the things on my own for some reason, which is not super great, but I enjoy it. So, but yeah, it's kind of come from, I work at Neat Corporation where we're making VR games, and like making VR games is very challenging in many ways, and one of them is that learning about headsets, learning about motion sickness, learning about vestibular mismatch and all that stuff that you need to read about. It's a lot, but it's really interesting, I think, to learn about how all of that works. So, yeah.
Vestibular mismatch. It's that your eyes say one thing and your ears say another thing, and you don't know why. You just know you don't feel good. Exactly. How do you put that into math? We know that that's a thing. It's basically like car sickness or seasickness. And it's why I can only do 15, 20 minutes of VR and I just need to take a break and almost just breathe. How can you solve that if you're all sitting around at the Neat Corporation going, yeah, that's a thing. Here's some math to fix it?
Yeah, kind of. Yeah. So what happens is that you see something happen, right? Like you are sitting in a car and you're reading a book. That's like a common case for motion sickness, or looking at a smartphone. That's a more modern take, I suppose. Anyway, so let's say you're in a car, you're looking down at something and you don't see the outside at all. Like the windows are like outside of your peripheral view. Okay. So what's happening is that you are seeing a mostly static world. The car is not moving relative to you for the most part. And then the world outside is moving a lot, right? There's a lot happening. So people get motion sick there because then there is that mismatch, right? You see one thing, but you feel something else. And then people can get motion sick from that. The motion sickness you get in VR is sort of the opposite of that. It's reverse car sickness, sort of, where you see a world that is moving if you're moving a character or something is happening with the camera in game, but you don't feel that at all. So it's the same. It's the type of mismatch, but it's reverse in terms of which one is moving, right? So the whole so what you need to solve is how do you move the player without causing vestibular mismatch, which is a difficult problem. So, in most games, you have some character that you can move around, or you look around, or, run around a level or whatever. That's really difficult in VR if you don't want to, get people sick. So, turns out the biggest problem is acceleration and expected acceleration. You don't really sense linear movement. So you can sense if you're changing your direction or changing your speed or velocity, but you don't detect just having a constant motion. That will generally not get you motion sick. So say you're standing on a train that's just moving forward linearly, then that generally doesn't get you motion sick, because then there's no mismatch. The mismatch is only in terms of acceleration or forces, right?
That's why it's more comfortable to be on a plane that's cruising and you can read your book. But when it starts to bank or make a big turn, you're just like, whoa.
Exactly. Yeah.
Interesting. So figuring out how to counteract that, there are now mathematical ways to understand those things.
Are the mathematical ones? I think it's more about physics, like figuring out, well, what is movement, what is acceleration, and how do we make that not happen, right? So if the only thing you can do is linear movement, then you need to incorporate that into your game. So okay, let's say we cannot move forward with a character continuously or something, but we could teleport, right? We could just instantly go from one place to another, and there's no acceleration involved there. It's just an instantaneous moment that happens. So that doesn't cause motion sickness. So then you're like, okay, so now we have some tool we can use to move throughout the world, right?
This is when, like I've done Skyrim in VR, and it's just awful. You're head bobbing, you're walking around. There's half a dozen different things that are making you nauseous. But then if you switch
that
it to
sounds
teleport,
awful.
it's horrendous. But then the teleport model that was kind of like discovered in VR is you throw a parabola out in front of you and you say, I want to be over there, and you go whoop, and then suddenly you're there. You've teleported.
Yeah.
This reminds me of some documents that I read about early filmmaking when they were trying to figure out whether or not a sharp edit or a sharp cut would confuse the viewer. Like, should everything be in a continuous cut, like our lives, right? There's no cuts when I live. Or if you have, here's a person on the screen and then I cut and now there's a person over here, would the brain be like, what just happened? And apparently we're really good at that. We're totally okay with lots and lots of fast cuts, and we absorb those things really quickly.
Yeah, which is kind of weird, right? You wouldn't expect the human brain to be fine with that because it never happens in nature.
Yeah, like I would expect the human brain to be totally fine with head bobbing while walking around in Skyrim, and I would assume intuitively or counterintuitively that the more walking in a game was like walking, the better. And in fact, the less it's like walking, the better, isn't it?
Yeah, exactly.
Interesting. One thing I wanted to ask you that was on my list, and it'll be a good way to close, is that one of my favorite animations of yours is the area of a circle one that we mentioned a little bit, where you have this circle, you look at the radius, you look at the circumference, and then you unfold it and you show the relationship between the area of a circle and the area of a triangle. You use something that's tau, the Greek letter tau, and I have not seen that before. I'm used to saying pi times the radius squared, but you have
Yes.
tau, and a lot of people were also confused by that. Is that an American versus European math, like how you're taught, or what's the deal with tau?
I wish it was as popular as that. So this could be like an entire podcast on its own.
Really, the podcast about tau.
Yeah, there's been sort of a little movement to replace pi with a different constant. Not really replace, I suppose, but when it comes to angles, to use a different constant instead. So if you measure angles, quite often you're probably used to measuring using degrees, right? You have 0 degrees, 90 degrees for a right angle, and 180 degrees, and then 360 for a full turn, right?
Right.
Scientifically, and quite often in programming, and whenever you're doing tech, and mathematically, usually you don't really use degrees anymore. There's another unit called radians, and the radians unit for angle has a different relationship for, what is a full turn. So a full turn in radians is the number of times your radius of any circle repeats around the circumference. So turns out that number is 6.2 something something, right?
Mm-hmm.
So, okay, so now we have this new way of measuring angles. It goes from 0 to 6 point something. So if you have this relationship, or if you use this angle, there's a really clean way to convert, to get arc length from angle and vice versa. There are many, many relationships that work out really well if you use radians instead of degrees. So what is that number? What is that 6.2 something? Well, you're probably familiar with the constant pi.
Mm-hmm.
So pi is the ratio of the circumference and the diameter of a circle. So here we run into this weird situation where we have defined our circle constant to be, using the diameter as base,
mm-hmm.
but our angle unit, radians, are using the radius as the base. So what happens is that if you want a full turn, that constant, 6 point whatever, is equal to 2 pi. So now we have this weird situation where we have a 2 there that is kind of ugly, right? You want a full turn to not have a constant of 2, because then you get run into all sorts of problems of okay, how much is a quarter turn? It's let's see, is it half pi? Is it 1.5? You get these conversion issues in your head. So you have this really weird unit. So, and this turns up in so many places in math where you have 2 pi just scattered throughout almost every equation out there related to angles. And then, you kind of run into this, why do we use this? Why do we define 2 pi as being a full turn? Why not have a single constant to represent a full turn, right?
Well, and you keep saying full turn. As a lay person or as a more lay person, I'm thinking to myself, pi is like the thing I associate with circles, but it's really half a circle.
Exactly. It's half a turn when measuring in radians.
So tau,
which is weird.
Oh, wait a second. So you said 6.2 something something. Well, pi is 3.1415926. That is tau. So this is 6.283. Da 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 da.
Exactly. So tau is exactly equal to 2 pi. So then you can take all of these 2 pi's out of our equations and just write tau. And the nice thing about using tau is that if you want a quarter of a turn, well, that's a quarter times tau. If you want half a turn, that's, half times tau. You get this very, very intuitive way of, thinking about angles using tau.
Whoa. See,
and something that
why are you teaching math?
Well, I don't know.
Cool. Well, you're teaching it on Twitch, and that's what's exciting.
I am teaching it on Twitch, and I also do it on Twitter, I suppose, but mostly on Twitch in aggregate, I suppose, because given my live streaming and whatnot, there's quite often people who come into the stream and they're like, oh, how much math do I need to know to make games? And then I usually talk for a bit too long about that.
Well, in fact, speaking for a bit too long, you did a really great math for game development live course. You just kind of pulled it out of thin air, and then ended up being about 4 hours. It's on your YouTube. We'll include a link for it. You call it an improvised live course. You also have a Patreon, and folk can find you at twitch.tv /AceGikmo, ACEGIKMO. I'll make sure, again, links to all the show notes. We're going to have a lot of great links on this show. You're doing a ton of stuff. And are you hoping to put all this together into one medium? So there's one link that we can go to learn more about the work that you're doing?
I hope I do that one day. I don't know when I'm going to do that. As for my math stuff, I have considered writing an online book about math. I think that one would incorporate a lot of the useful math animations that I do, because I do a lot of math animations that are just art. But yeah, so I have this idea of, kind of reimagining a textbook and sort of thinking about, okay, what would a modern textbook for math be, and how can you make this practical instead of being, technical and covering all the topics like a Wikipedia page, right? Mm-hmm. So yeah, I've been really excited to try to do that and try to, make something that feels more modern and interesting.
That would be cool. Well, for now, I'm going to enjoy your Twitch and your Twitter and look forward to this theoretical future math book. I really appreciate you chatting with me today.
Yeah, thank you so much for having me.
We've been talking to Freya Holmér. You can check her out at the show notes and at Ace Gikmo on Twitch. This has been another episode of Hansel Minutes, and we'll see you again next week.